I know more than they do about this stuff. Well, we have 1 more minute if you have any. Well, actually, no. 5 seconds. As of 8:30 a.m. today, the class has 65 enrolled students. Doesn't look like 65 people. Anyway, as you know, I think I didn't tell it yet in PY106. You can bring a horse to water. You can't make it drink. So, question. What do you think? You should imagine an actual measuring device, a multimeter, that big thing or small thing with wires. And if the sentence says voltage between 2 points, the voltage has many different names as well. It's a potential difference, magnitude of change, potential, and it also has a second name, drop or rise. So voltage drop, voltage rise. All those things mean exactly the same thing. All those words have exactly the same meaning. Measured between 2 points. And the points here are A and B. So if you connect a multimeter, you actually can draw. Drawing always helps to visualize what is happening. So we have a multimeter. We set it to measuring voltage DC and have 2 wires. And that's it. And we read the number. What will we read? Yeah? So let's see. We'll get some distribution, and the peak of the distribution says 10. Well, in this situation, we can apply different ways of thinking. For example, just a rule which says parallel means same voltage, which is 10. How do we know? We have eyes. But also it's handy to do it again to kind of prove this using our general approach, tracing the potential, electric potential. Oh. 0 volts. Now, it changes here. Now, if I go in this direction, and I can choose any direction for my imaginary walk through the bulb, should potential drop or rise? That's actually V, 0 volts. Again, to answer this question, we should look at the direction of electric current. And electric current outside of the battery goes from plus it does go through all the bulbs like this. So in this circuit, the direction of electric current is, that's what we call clockwise. So this red arrow represents electric current through that particular bulb. And the opposite to that, potential rises. So it's the new potential here should go up to here. Actually, even through the bulb, it should remain the same. But potential at point A will be different. And we actually can calculate everything, and we will do on the next slide. But for now, if you calculate those potentials and calculate actual difference, you will get 10. Well, let's calculate what we need to calculate. First, of course, we can just redraw the circuit without element, which doesn't make any difference. That bulb doesn't make any difference. It doesn't affect the electric current. There is no current through this bulb. So the equivalent circuit looks much easier. Bulb number 1, bulb number 2, bulb number 3. And this bulb has voltage across it, 10 volts. And now, again, we have two options. Number one, actually calculating things, proving what we should know already, that if we have the same bulbs and they have the same electric current through each bulb, they should experience the same voltage across. Even we don't know electric current, I. Still, because it is the same for all three bulbs, the voltage should be equal to I times R, same I, same R, same voltage, which means this has to be 10 volts, this has to be 10 volts, and now 10 plus 10 plus 10. The battery should provide 30 volts. Technically, what we should have done is numbering the bulbs 1, 2, 3, and then writing the same equation 3 times, a specific equation for each bulb. Come on. Number 1, then delta V2 should be equal to I2 times R2, then delta V3 should be equal to I3 times R3. And now we say, hey, I1 and I2 and I3 are the same. R1 and R2 and R3 are the same. Hence, they all have to have the same voltage. Well, of course, now we have to close the switch and see if anything changes. When the switch is closed, of course, the total resistance changes. In order to keep the same voltage, we would have to use a different battery, so we cannot say 30 anymore. But again, we know that let's call them 1, 2, that was 3, so that now becomes 4. That bulbs 2 and 4 share the same voltage, 10 volts. 10 volts here, 10 volts there. Does it mean this voltage is also 10? Not anymore. Again, we can apply different ways of reasoning. For example, what we know for sure, that this electric current and this electric current are different, and we know how. Which is higher, which is lower? Electric current is a number. For any two numbers, only have three options to choose from: greater than, equal to, less than. I couldn't hear which is higher. You say electric, and then I can't hear you. Okay, that's a valid hypothesis, so let's call it number one. Higher means like this. Well, okay, let's call it number two. Let's call it number three. Let's vote. If you are for the option number one, please raise your hand. Well, you have to be consistent, you said it. Even if you've changed your mind, you still... So for the option number two, please. You're late. You have to raise your hand. Doesn't matter, just raise your hand. Thanks. Option number one. You didn't raise the hand at all. So, okay. Option number three. I tricked you. Now, what is happening to electric current here? You see? It's like a pipe. And then it splits. You have many charges here. What's happening? What's happening? They split. So the less electrons travel. That's it. It's just a same old junction rule. So that's the right answer. But we can make an extra step. We can write an expression, mathematical expression, how to relate these two electric currents because of this magic word. If all the bulbs are identical, what does it say about current number two and current number four? Equal, they must be equal. Same voltage, same resistance, same current. For bulb number 2 and bulb number 4, everything the same. So if we add them up together, which is we should get the original current. The original current just evenly splits between two other currents. So now we can look at the equation. That's a general equation for any bulb, for any device. But if we write it twice, and now if we account for the fact that bulbs are identical but currents are different, we make a conclusion. What conclusion? Anybody? What conclusion can we make? Yes, you want to say something, say something. See something, say something. Well, the conclusion we are searching for is about these two numbers, voltage number 1 and voltage number 2. The whole process was leading us to making a conclusion about these two numbers. They cannot be equal anymore, but they have to be related, because electric current here is twice higher and the resistance is the same.
Voltage 1 is 200.
Which gives what number? 20. That's it. That's the conclusion. We just have to write it down so we wouldn't forget. And this is a very good rule to remember. Same resistance, higher current means higher voltage, How much higher? Well, same coefficient. If the current is twice higher, the voltage will be twice higher as long as bulbs are the same, the resistance is the same. So will be equal to 2 times delta V2, which is 20 volts. And now we just count 20 plus 10 plus 10 plus 20, 40. No. What did I do wrong? Today, I'm going to be making many, many mistakes. Not on purpose. It's just Friday the 13th, so I just made one. Do you know what mistake did I make? 20, 10, 10, 20. Some of the parallel, you can't count them independently. It's one single element. So you just count 20, then 10 once for both, and then 20 again. Which gives 20, 20. Plus I added them wrong. I said 20, 10, 10, 20, 40. That just can't work. So 20, 10, 20, 50. I have, well, okay. EMF, that fixed voltage, should be equal to 20 plus 10 plus 20, 50. So when all elements have the same resistance, we have shortcuts we can use, like this rule. If the resistance is the same but current is twice higher, the voltage should be twice higher. Question. So now, again, we have 6 identical bulbs connected in a certain way. Question is, what would you say about the brightness? Bulb 4 and bulb 6 connected. How? If you look at the bulb 4 and you look at the bulb 6, are they connected in series? Definitely no. In parallel? No. They would have been connected in parallel if bulb 5 didn't exist. But the bulb number 5 exists, so they not connected in any specific way, 4 and 6. But yet, if we look at the circuit and figure out what's happening to electric current or to the voltage, we should be able to say something about the brightness. Now, the brightness is an optical feature. That's a description of a perception, of human perception of something, but we know it's related directly to the power of the bulb and the actual power the bulb dissipates, not the power we read in it, because all bulbs are identical. If we read what's written, we will read the same numbers, which means they would be equally bright if they all would have been connected in parallel with each other. As long as connection is different, the actual brightness depends on actual power, and power well, can be calculated differently. And again, in terms of brightness, this is the least convenient expression. When all bulbs are identical, they have the same resistance. So which means higher voltage, brighter bulb. Or higher current, more power, brighter bulb. So you can choose either of the approaches. You can think about electric current traveling through these two bulbs and say something about electric current, or you can think in terms of the voltage across each bulb and say something about it. If electric current is the same, and because the resistance is the same, power automatically is the same, brightness is the same, etc., etc. And as you know very well, knowledge is power. That's why knowledgeable people are bright. Pure physics. All right. We have a winning answer. So I would prefer using voltage. It's easier because in this particular circuit, we actually don't even care what is happening outside of it. If this voltage is wherever it is, how do I call it, delta V6, it has to evenly split because those bulbs all have exactly the same resistance, so that should be 1/2 of delta V6, and that should be 1/2 of delta V6. Less voltage, dimmer, dimmer. Also, of course, we could think in terms of electric current. Electric current here has to split because it's a junction rule. But more resistance means lower current. The top branch has more resistance, twice more. So I4 will be less than I6, less current, dimmer, higher current, brighter. And of course, now probably just have to rank all of them. Okay, that's the answer. Not just to rank, even do more, calculate actual voltage. Okay, we can do that. Can we? When we have to solve a problem, we have to apply certain knowledge. But before that, we have to fulfill two conditions which have nothing to do to physics. Number one, we have to believe that the problem has a solution. Number two, we have to believe that we are capable of solving this problem. Otherwise, we're not going to do anything. We're just going to pretend, fake, that we're doing something and thinking, why the hell do I do that? So, do you think this problem has a solution? Do you believe you can solve it? Okay, solve it. I'm going to give you some time. You can talk. And I will ask maybe a question about the voltage across bulb number 3. So. Just ballpark, how much time do you think you would need to finish this problem? Anybody? You moved it, you. All right, I'll give you 4. I'll be back. Go ahead. Ask everybody what they're doing and do the same. Hey. That's my favorite time. They work. Yes. It's Friday, so why should I work anyway? All right. Tick, 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 tick. Apples. Benjamin Franklin said just one apple a day.
Well, just making sure.
Okay. Okay. I think it's like one more minute. So I've promised to ask you about the voltage number 3. You don't have to whisper, you can speak out loud. So everybody who has a number for delta V3, please just wave your hand so I could see. Okay, thanks. Thanks. All right, I'll wait a little bit longer. Did you find delta V3? Okay, what is your answer? 62 volts. I don't know the answer. I knew it yesterday, but I have very short memory. Anybody else, please? If you have a different number, please tell me. Yes? 60. Okay. If you have a different, not 60 and not 62, please tell me. Yes. Maybe. But I would expect some round number with a 0 in the end. Just, I remember. Now, there is a trick, a hint, which I find very handy. So, you don't have to use it. But I know that some of you don't like algebra. She likes you. If we believe this problem has a solution, and if we see no other values provided except voltage of the battery, that means all other values should matter at all, should not affect the result. And if they don't matter, if they shouldn't affect the result, that means any value can work. Anyone, I mean not anyone, any one. So you can pick any value for what? Not for resistance, of course, because it's the same for all. And that will give you a way actually calculating numbers, just calculating. Different value of R will affect electric current, but if there is no question about electric current, it will not affect final question about the voltage. So that's one way to do it. And that's what I want to do for now, and then we can do it algebraically. I pick 30. This bulb has the resistance of 30 ohm. If this is 30, what will be the resistance of these two together? 15. And this is a time-saving technique. We know when elements connected in parallel, same resistance. So we just divide the resistance of a single by the number of elements, 15. Now, this is a little bit trickier, but we've done it many times. We can do it one more. The resistance of this whole part of this circuit will be equal to 1 over, well, I used 30. You could have used R, yeah, plus 1 over 30 comes from this. What number comes from those two? 60. 60. And that will be common factor is 60, 2, 60 over 3, 20. So now, I can set any voltage as my unknown, since I started from, let's call it X volts. In that case, that's the most important question now. What number should I write here for the voltage across that resistor in terms of X? A half. That's exactly right. That's what we need to see already. If we have elements connected in series, the voltage is equal to current times resistance. And now we use this equation differently because they share the same electric current. The resistance defines the voltage. More resistance, higher voltage, less resistance, lower voltage. The resistance is a half, voltage is a half. And so that's the voltage here. what should I write for the voltage across 20 ohms? How do I get from 30 to 20? What mathematical operations should I make? Do, perform, enact. Yes, I have to take 30, I have to divide it by 3, and then multiply by 2. But, as we know, if we add them up all together, all those voltages together, what number should it be equal to? 130. This is an equation we can solve because it has only one unknown. We just need to figure out the common denominator. Common denominator will be 6, right? So 6x 130. That's going to be 3 plus 6 plus 4. X equals 130 over 13 times 660. So you should check your math. Maybe I'm not sure what went wrong, but the answer is supposed to be 60 for this bulb. And of course, automatically we get 30 volts and 40 volts. And now, okay, let's write them down. This is 60 volt difference. So this will be 40. This will be 30. Now, what voltage should I write for this single bulb number 4? 20, a half of 40 here, a half of 40 here. So now we can rank all the bulbs according to the brightness. The highest voltage is here, that's the most bright bulb. Then this one. Then those two equally bright but dimmer, and those two equally bright but even dimmer. Any questions? All right. Answers. All right. If you don't ask me questions, I'm going to ask you a question. Please read the question and choose your answer. I should have told you before. I wanted, but I forgot. Okay. Once in a while, I want to grade your answers. But since I didn't warn you in this situation, I'm not going to do that. But sometimes it might happen. This is question number 4. I should have graded it. Already majority is wrong. Well, you already know yes is a wrong answer. Now, can you say why? Anybody? Give an idea. Doesn't have to be correct answer. Any idea. Yes? Absolutely right. according to a definition of a voltage, it's related to 2 points. Electric potential is related to a point. The voltage is equal to a difference between electric potentials at 2 different locations. That's it. So we need to know a definition. If we said yes, we don't know the definition of voltage. All right. Now let's just go through this circuit. And what do we have to calculate? The voltage. All right. Maybe not going to do all this because it's very similar to what we've done before. But the first thing to do, of course, is to redraw the circuit. Just draw it nicely, neatly, because this just ugly. And how do I want to redraw it? Well, okay, let's keep it vertical. So no acute angles, just easier to look at the things when everything is straight. Now, as you can see, this circuit has 2 types of bulbs, square bulbs and round bulbs. And what we know about those bulbs, they have different resistance. A junction point. And the voltage of the battery is 10. It's hard. Okay, let's do it algebraically because we did it with a number. Again, the question is about voltage, and the voltage is given, so we need to make a connection between a voltage, EMF of the battery, and the voltages, individual voltages. And because we believe the problem has a solution, it means the actual value of R doesn't matter, and we can set it to any number. I don't know. Again, you could do it 30. Why do I like 30? Because very often in a problem like that, we have multiples of 2, 3, or 5. So 2 times 3 is 6, 6 times 5 30. So just make calculations easier if you have no calculator on hand. But if you have a calculator, any number would work, doesn't really matter. But if we do it algebraically, this is R, this is R, this is 2R, this is 2R, this is 2R. Now we can algebraically usually means simplify the circuit. So for example, 2 bulbs on the left, we can replace them with 1 bulb, 2R over 2 is R. All right, now well, what I see is 2 bulbs in series, R and R. I can replace them with 1 round bulb, 2R, 2 times R. Okay, now I can see what I can do next. What can I do next? These 2 are in parallel, I can combine them together. 2R over 2 is R. I can make an extra step, but I don't need it because now I can start. I can start talking about the individual voltages. So this voltage, which is 10, should split evenly because we have just two elements with the same resistance. So this voltage equals 5 volts, 5 volts. So that's going to be 5 volts here, 5 volts here, 5 volts here, 5 volts here. And now it was 5 volts for both, but now R and R connected in series, so it splits 2.5 volts here, 2.5 volts here. And now we go to the original 5 volts, 5 volts, 2.5 volts, 2.5 volts, 2.5 volts. That's it. Okay, I think that's my last circuit for today. So, question. This is about what we cannot do. Electric potential at point B can or cannot do we have a power? If you think we don't have that power, choose one. If you think, yes, we can, choose two. Oh, there are more answers. Don't choose any of those. Well, yes, we can, of course. We can choose any point to any potential. It doesn't have to be zero. We can choose any point and set it to any number. And relative to that number, we can measure and calculate all other values. So here, I wouldn't choose B to 0, because I can see the lowest potential should be here. This point is connected to negative electrodes of both batteries. So this is where I want to choose 0. What does a battery do? The battery increases potential by the EMF. So from here to here, potential increases by 36, from 0 to 36. This potential is 36 volts. See, I'm just writing numbers now, like I did in a previous problem. But I need to remember what it represents. All these numbers represent voltages. And now I'm writing numbers which represent potential. It has to be set in my memory cell somewhere, in a different memory cell. Potential, voltage. And so, again, oops. This potential will be 0, but this potential will be 12 volts, because that's what the battery does. And electric potential here and here still will be 12, because the wire doesn't change electric potential. Electric potential here, 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 still 0. Now, what is happening to electric potential when we go through this bulb? And electric potential, because it is a number, might increase, remain the same, or decrease. And you have to make a choice. It might be important. For example, someone, I don't know who, could ask you, what is the potential difference between these 2 points? In that case, you would have to know electric potential at point B, you would have to know electric potential at point C, and then calculate the difference mathematically. So, anybody, please tell me. Does bulb number 2 change the potential? That's a yes or no question. And if it does change, how? So what do you think? Does the bulb number 2 change the potential? Moving doesn't help. I'm looking right at you. Does it? Follow your feeling. Say yes or say no. At least it's 50-50 chance to be correct. You can't say maybe. You always have to project confidence, even if you're wrong. Maybe is not projecting confidence. So the answer, of course, is based on the application, straightforward application of the Ohm's law. Delta V should be equal to I times R. Delta V is not zero if both I and R are not zero. If I is zero or R is zero, delta V is zero. Now, for the bulb number 2, is the resistance equal to zero? For the bulb number 2, the resistance, zero? No. Current. Is there any current through that bulb? No, because the switch is open. That's where physics is, not mathematics, physics. So electric current number 2 is zero, hence delta V 2 is zero, hence V remains constant. There is no change. So electric potential here at point C is still zero. Potential difference between points B and C will be equal to 12 minus 0, 12. But we don't care about that. We already answered the question about potential difference. So this potential difference between A and B is also 12, 12 minus 0. What else can we calculate if we wanted to? Well, there is electric current through bulb 1, definitely. And how do I calculate electric current number 1? It should be equal to the voltage across bulb 1 divided by the resistance. How do we calculate the voltage? According to the definition, which has to be equal to the difference. 36 minus 12 divided by 8. That's what the voltage is. 36 volts on the left, 12 volts on the right. Potential difference is an actual difference. What does it give us? 3, right? 12, 3 amps. Oh, that's my last circuit. Well, but we know what to do. If we close the switch, that doesn't affect any of the main potentials. This potential still can be set to 0. So 0, 0, 0, 0, 0. The battery increases it to 12. VB equals 12 volts. This battery increases the potential to 36. V plus equals 36 volts. So this potential difference still delta VB, delta V1. Yeah. Delta V1 equals 24 volts. So it doesn't affect current 1, but now current 2 is not 0 anymore. I2 now just will be equal to this potential difference, delta V2, which is 12 over 2 amps. Now let's see actually. I2 I1. So there has to be some current which goes through the battery. If this current was equal to 3 amps and this current is equal to 2 amps, the junction rule tells us that current through second battery should be equal to 1 amp. And because the battery has no resistance, we cannot apply the Ohm's law, but the junction rule tells us that this electric current should split. So it doesn't disappear, it still has to go somewhere, and it goes through the battery. The battery wishes electric current would go that way, but this is much stronger, so it actually makes electric current through the second battery travel opposite to its natural direction. It happens. Yeah. A strong battery, a weak battery loses. Well, are we done? Yes, we're done. Now it's your time to start asking questions, because if you ask questions, I give you answers. If you don't ask questions, I've got something. Yes. Any question? You have to speak up. This case? You have to ask a specific question. If you say, I'm lost, that's not a question. That's a statement about your state. I can't help you. If you have a specific question, that's what we can discuss. Yes?
About this one?
Yes.
So, Aaron, did you say that all being pushed by the larger battery?
Yeah.
The second battery, is it adding any current at all, or is it just
What do you mean?
like is
The battery, this battery affects this voltage. You take it out, and this voltage will not be 12 anymore. The battery is responsible for fixed value of potential difference between the electrodes of that battery, no matter what is happening outside many other batteries or devices. That's what battery does. If you read the number 12, you take a multimeter, you apply it to the electrodes of the battery, you will read 12. And here you will read 36, because that's what the battery does. The rest is, well, wherever it is. Yes? This is the current which goes through the second battery. 1 amp. Yep, because electric current obeys the junction rule, the law of conservation of charge. If 3 amps go here and only 2 goes there, it cannot disappear. Yes? That I don't understand. If you take it out, the voltage across the first bulb will change. So the battery does something. The battery sets the right electrode of the bulb to 12 volts, the potential at the right electrode. If you want to see what's going to happen without the battery, I would just do this. Okay, let's see what's going to happen if there is no battery number 2 at all. That's going to be a new circuit, and in this new circuit, this is 36 volts and 8 ohms, 6 ohms. So now electric current will be equal to 36 over 8 plus 6. 36 divided by 14, 2.57. 2.57. Now, if you want to calculate, let's say, this voltage, the voltage number 2, it will be equal to current times 6, 2.57 times 6 times 6, 15.4. And again, if this voltage is 0, 0, 0, 0, 0, 0, 0, this, this potential is 0, 0, 0, 0, 0. This voltage, 15.4, makes this potential higher by 15. So this electric potential now will be 15. But as soon as you insert the second battery, that potential becomes from 15 to 12 because the battery does it. This is just an illustration. It's not related to homework because there is no single problem on a homework with 2 batteries. That's all I can say. Questions? Yes? The exam will be covering everything from the first minute to the last minute of this lecture, theoretically. Except if we begin the new material. Yes? That's an important difference. So, first of all, again, in physics, everything is based on a law or a definition. Nothing else exists. And there is a law of conservation of energy which led us eventually to something which has been called potential energy of a charge in electric field. Standard variable for that is a U, capital U. And again, this is the definition of this variable. Potential energy is that thing which can be used to calculate the work done by electric field on a charge by subtracting final value from initial value of that thing. That's what it is. But then we say, okay, let's say we know potential energy, no matter how. In that case, potential energy of a charge divided by that charge, which is an equivalent of potential energy of a positive 1 coulomb charge, that's named. Named means we gave it a birth, we named it, that's it. Electric potential. That's a definition. However, now, if we combine these 2 definitions, a definition of potential energy and a definition of electric potential, we get a convenient equation, technically, theoretically, mathematically convenient equation, which relates the work done by electric field on a charge, that charge on which the work is done, and the potential difference. How did we move the charge? How did we bring the charge from initial location to final? Doesn't matter. It doesn't affect the work. It only depends on initial and final values. Does it depend on time? Doesn't matter how much time did it take. And in a couple of problems at home, you also use the fact, well, this is a specific work done by electric field, but if nothing else is acting, only electric field on the charge is acting, in that case, the change in the kinetic energy, which has to be equal to the net work done, also will be equal to work done by electric field if nothing else is acting, which is this. And this is kinetic energy final minus kinetic energy initial. Yes? Yes, V. If you ask a question, that's a wrong question. The right question about any variable, including this, is what can it be? And then we have several choices: speed, volume, Voroshilov, potential. And then, depending on the situation, you have to make the right choice. If it's electric field, and a charge, well, normally, this is the most important part. That means V means electric E, potential, would have been volts. And the same reasoning goes for any letter. So if in your memory you have only one possible meaning of this letter, that's it. You cannot solve a problem where that meaning is not applicable. That's why you have to have in your memory all possible meanings. That's the only way to choose the one you have to use. And if you use a wrong meaning, well, you don't know it's right or wrong until you finish the work. You have to try, follow your guts, your idea, but if it doesn't work, the first question to ask, do I use the right definition? Do I use the right meaning of this or that variable? Questions? Yes?
The brightness depends on power.
Yes, directly. More power, brighter bulb. Questions? There's one thing, since I started it, I want to say about meanings. Normally, when we say something, we assume that what we mean is exactly what we say, and that everybody else has exactly the same meaning listening to our words. And normally, that actually leads to misconceptions, misunderstandings, fights, and wars. Eventually, might be. So, that's why we need to be conscious about all possible interpretations of every word we're saying. There are two human practices where it's developed to a higher accuracy: science and law. In the law, every word must have a very specific meaning. But a good physicist can become a good lawyer, but a good lawyer cannot become a good physicist. Questions? No questions. Okay. She's saving you all.
This one's also about wording.
Yes.
So on the equation sheet, a lot of the equations will say like magnitude of electric field on a charge Q, but on a charge, and that also is referred to as the point. Give us a graph and say, okay, find the electric field at point B, and point B is an electron or a positron. It's not anything. It's just like a point. We'll use those same equations.
Probably have to look at the equation sheet eventually, because I think what you're saying is wrong. Because, again, in terms of wording, electric field might act on a charge at a certain point, but the equation is for the magnitude of electric field of a charge at a point away from that charge, which generates that field. This is a charge. It creates electric field around, and at certain point away from it, at a distance r, this will be the magnitude of electric field generated by that charge. We call it a source. But there is magnitude of a force acting on a charge from electric field. And that's a different equation. This is a different charge. This is a test charge, which we place in electric field generated by a source charge. And that test charge feels the electric field in terms of force. And there's another equation which says a different wording: magnitude of a force between two charges. And if we go further, so there is also electric potential of a charge. And even we didn't talk about it, but there is an equation for electric potential energy of two charges. We used it once to derive, no, we did it for gravity. Yes?
So if we had three charges like in a triangle, had a point in the middle, and it was saying, okay, find the net electric field on this point.
Yes. In that case, if you have, say, three source charges, Q1, Q2, Q3, and you are asked to calculate electric potential or electric field at a certain point, in that case, you have to use the superposition principle. Well, for the potential, it's easy. Just add numbers. But for electric field, it's not so easy because you have to add vectors. So you have to draw, well, the equation is this: net equals vector number 1 plus vector number 2 plus vector number 3 And if you need to add vectors, you have to draw all those vectors. So let's say, just for the sake of a specific example, positive, positive, negative. In that case, how do we draw vectors? Away from a positive charge, E1. Away from a positive charge, E2. And toward the negative charge, E3. And then the net electric field will be equal to this arrow plus this arrow plus this arrow, or maybe something like this. Numbers. Vectors. All right. If you have no questions, we can finish today. I'm not going to start this today. Yes?
Electrons move from, say things move from height to low times low.
We,
Proton, right?
no. Protons never move. That we say about fictional positive charges, which could have been moving if we had them in a wire. Positrons. Fictional, imaginary positive charges. They would have been moving from a positive electrode of a battery outside of the battery toward the negative electron. Those are fictional positive charges. Would be moving like this. And that's what we call electric current. And actual physical particles, electrons, travel in opposite direction. They have velocity. An electron here has velocity in opposite direction.
So an actual electron goes from low to high.
Yep. This is a fictional positive charge from high to low. It basically travels in the direction of electric field outside of the battery. Electric field kind of pushes them down. That's it. Nothing else. Any questions? All right. I'll see you on Monday. Well, no, I have my office hours also. Cannot hear you. COM 101, College of Communication, first floor, big auditorium. It's kind of in the middle of the, what? I will send an email. Also, I shouldn't. College of Communication. It's not this building, it's building after the building. I just park it over here. No, I mean just right by the door. Yeah, thank you. Yes.
At 9, okay. I was at last semester, it was like 30 minutes after class usually started.
No.
Okay.
Our class was at 8:30 and the exam was at 8:30.
Okay. I mean, it ran so
Bringing my ID so I can get some.
Yeah, I'm gonna just move my stuff and go to the room. Home 101.
Home 101?
You know where it is?
No.
At the College of Communication. You should search for that. It will on the map. It's very close to this that way.
Alright, take this direction.
Just go, yeah. Comment.
So that it has the green lawn.
Okay.
That's the Starbucks. So is that where the green lawn fountain is? That's
Okay.
the
Alright, thanks.
Tick, 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 tick. See you Monday.